So today, this workshop is on sublinear. I'm going to go extreme sublinear and talk about logarithmic. Okay, this is about logarithmic time prediction, and the problem is extremely simple to state, but it's hard to wrap your head around because there's so many hacks people use to try to get around this problem that you always think about the hacks rather than the actual problem. Okay, so the problem is you see some features, you want to make a prediction, and then maybe you see the true label. Okay, so this is sort of an online setting. It doesn't have to be online, but the goal here is to minimize the error rate. And so far, we're talking about just standard binary classification. You want to minimize the probability that you make the wrong prediction. But then we have this caveat down here. We want it to be fast, right? And that's kind of the core caveat. This is the way that everything is different from what's come before. And then now the question is, why do you care about this sort of problem? And the claim is that, well, really you care about it quite a bit because there are very natural problems which have this structure. So X would be the query, and then the prediction would be which web page you care about. And there's some, I understand there's some economic rationale for trying to respond to queries efficiently. So if you take a look at a real search engine, the way it works right now, machine learning is kind of a small piece that happens towards the end of the process. Is this big information retrieval engine which lies underneath. And then there's this machine learning thing at the end which kind of reorders the top end results for n relatively large, but not nearly as large as the number of web pages. And without the machine learning, it doesn't work, and without the information retrieval engine part, it doesn't work. But it's kind of weird because you have these two systems that are really not very similar, somehow glued together, and because it's actually a fairly important problem, people work on figuring out how to glue things together. But you might hope to have an algorithm which is just a clean algorithm that just kind of nails things all the way through. So I'm not going to claim at all that we're getting close to that, but that's an example where you want h of x fast. And then there's another one here, which is sort of like the Facebook problem. Who is that in the photo? Right? So maybe there's on the order of 10 to the 10 people in the world. You have photos, you want to know who's in the photo. A human could actually do this in some sense if they could actually manage to at least get hints about who it might be to start with. But learning algorithms can't really handle this right now. Okay, so this is another example where you might want to have h of x fast. And you can think about this machine translation as a very common case. So there's a lot of tricks here. One trick is you only deal with problems where k is small, the number of classes is small. That's a standard trick in machine learning. Okay, so that makes it easy. And if you take a look at existing solutions in machine learning, typically they're order k, right? So you want to choose one of k things. Well, you build a predictor. Is it this class or not? 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 You evaluate all of them, and you choose whichever one is gets the highest score. So that'd be a one against all predictor. Okay, so that's a trick people use. Another trick people use is they say, oh, look, there's really a hierarchy of some sort. And now, instead of trying to predict one of many things, I say, well, I'm just going to predict which way to go at each root in the hierarchy, at each subtree in the hierarchy. So that's it's basically using trick number one repeatedly. There's an issue with that approach, which I'll come back to, but this is pretty near solved. And there's another common solution, which the vision folks like quite a bit. The idea is that you have some sort of complex shared subsystem. So it's shared by all the classes. So the process of doing an evaluation is amortized across all the classes. So that's the part from here to here. And then you just have a simple prediction at the output, right? So that's not logarithmic time, but it is at least amortizing a lot of the complexity of the prediction process. It's still going to be linear time because you're going to have a linear number of outputs at the end, and that can become a problem, partly for state reasons, but also for computation reasons. Okay, so that's a trick people use. There's more tricks. I'm showing you the machine learning related tricks, but of course, there's ones that aren't even machine learning related. There's also structured prediction. So the idea here is you want to predict some joint set of things. Like here's the dependency parse of a sentence. Which things depend upon which other things in a sentence. So that's a complex prediction, and there are ways to decompose the problem or finesse your way around the fact that you're trying to make this big complex prediction so that you make a bunch of individual predictions. So in particular, if you have label information available, you can say, so given any partial prediction, there's a way to kind of fill in the rest of the prediction such that you'll minimize your loss. The goal is always minimizing our loss. And now you can try to learn a policy for for filling in the prediction so as to minimize your loss, using as advice the policy that you might form given label information. We have a tutorial about this at ICML. So that works. It works pretty well. But you have to have some existing structure in mind when you're thinking about using these techniques. And if you don't have that structure, or you don't trust the structure that you have in mind, then maybe this isn't the right way to go. This is another fun trick. People like GPUs a lot these days. And when you think about it, I mean, a GPU is pushing, so teraflops is 10 to the 12, 4 teraflops is actually closer to 10 to the 13. If you have 10 to the 13 flops and you're choosing amongst 10 to the 10 faces, it doesn't look so bad. You have 1,000 flops per face. And that's, it's an approach which kind of works. But it's still, think of the environment, global warming. We're trying to minimize the impact of the environment. There is some fundamental amount of energy required in making these predictions, and you would just like to, figure out, do you really need to spend OFK time? Even if you can do it, should you do it? I guess I've had some conversations with people at some of these big companies, and they're like, oh, well, we can just do a MapReduce job and run something on 10,000 machines, and you can do that, but do you want to do that? I mean, I don't know. It seems like it's much more elegant if you can figure out how to do it on your laptop, right? Okay, so now the question is, how fast can you really hope to go? And there's various answers you can come up with, but the one that's really hard to avoid is logarithmic time. So there exists multi-class classification problems where achieving zero error rate requires something like log k time to train or test per example. So this is all on a per example basis. Okay, so the proof is very simple. You just say, look, I'm going to create a learning problem. I have x and y. Y will be uniform on 1 to k. And oh, look, it's already log k because that's the entropy, right? So if you need to spell out the bits of the answer, it's log base 2 of k bits. Can't do better than log base 2 of k. Okay, so that's a goal to shoot for. And then the question is, how close can we get there? Okay, I guess here's a graph where I cleverly undermine my own thesis, because instead of using like a linear plot, I use a log-log plot. And then exponentially better looks linear, but it's actually exponential, right? Exponential is really important. I mean, I don't know. I spent some time trying to speed things up, and the most satisfying examples by far were times when it was exponential improvement. Okay, so there's various approaches people have proposed for trying to get fast prediction inside of machine learning. And now I'll just kind of go through some of these approaches and claim they're not it, and we'll think a little bit about why. Okay, so sparse accuracy output codes. The idea here is that you create something like log k binary vectors. So I is the identifier of the vector, and y is the label. So these are going to be 0, 1 bit vectors. And then you train each of these, you train a classifier for each binary vector, which tries to predict whether or not the label is something for which the bit is 1, right? So it's in the set of labels defined by the binary vector or not. Okay, so it's a nice approach. And then you predict by finding the y with minimal error. So this is generally not logarithmic time. Do you know why? Well, this is completely amortized, so it can't be step 1. This one, we're training log k binary classifiers. As long as our classifier just is unit time per example, that seems okay. So the problem is here. Typically, the codes that people try to work with don't have any of the structures which allow you to do fast decoding. And that's often a necessary trait of the problem because the optimal code depends upon the problem in a manner which is just not true for information theory. I think in information theory, you can rely upon independent errors, and that allows you to succeed computationally with codes that just would not work effectively here because typically errors in these different log k classifiers are correlated. Right? There's just hard instances, and it's tough on those instances. Okay, so typically prediction here is omega of k. Okay, so here's another approach people use. Step 1 is you look at the confusion matrix. Every time you predict this, what is the truth, right? And then you do some sort of partitioning. So maybe you get the second eigenvector of the graph implied by the confusion matrix, right? And then that gives you a partition, and then you can recursively partition in order to create a hierarchy over your classes. And then, oh look, we have a hierarchy, and then we can just apply the small k solution. So that's nice. This is also not logarithmic time, and the question is why. Somebody's got to be brave. Yes.
It might not be a balanced tree.
Might not be balanced. Oh, that's a good one. That's a real issue, actually, when they're using these eigenvalue approaches, because it's not really necessarily balanced. I claim that it's still not logarithmic time, even if it's balanced.
The matrix?
That's right, the matrix. This is the step where people go, oh, we'll just run on 10,000 machines. But that approach breaks down when you have 10 billion classes to do. It works fine at 10,000 classes, but at 10 billion, it starts to break down. So we want logarithmic time both at training time and at test time, because I think in the end, the exponential gap is just too large to brute force at training time, even if you manage to achieve it at test time. Okay, so oh, this is a clever trick. This is when you're trying to do one against all classification. You want to train k regressors. And now instead of, so typically what happens when you're doing one against all is you have the class that you want to train. And you say, oh, the label here is 1. And then you have all the other classes, and you say, oh, the label for each of these is -1. But there's a really nice trick here where you do unnormalized learning. So instead of picking all other classes, you just pick one at random. And you say, oh, the label here is -1. And now you can't trust the scores to give you a reflection of the probability unless you play with things a little bit. But it's still the case that this is kind of a proper thing to do as far as classification. So you train the regressor for y with x and 1, and then you train some other y prime with x and -1, some other uniformly chosen y prime. So that's super powerful in terms of your training time, because your training time now is constant per example. Or maybe we call it logarithmic if you really want to count the bits of the label. But this is still not logarithmic time overall. So it's kind of disappointing. There's lots of ways to not succeed. And now let's try to think about how we can succeed. But before we can succeed, I think we have to actually rewind a little bit. And I said, oh, if you have a hierarchy, it's actually easy. But the truth is, if you have a hierarchy, it's not actually that easy. There's some care that must be taken when you have a hierarchy. And that care is shown here. So suppose you have 3 classes. You have class 1, you have class 2, you have class 3. And suppose that the conditional probability of the classes was 0.4, 0.3, and 0.3. Now, if we want to do something in logarithmic time, we maybe want to start thinking about tree-like structures, things which allow us to do divide and conquer. So we're trying to do some sort of divide and conquer. We go, I'll have 1 on one side, and I'll have 2 and 3 on the other side. And now you want to build a classifier at the root, which says, is the label to the left, to the right? Okay, so we're trying to learn a label, or predict a label. And let's say we have a really good classifier. And let's say this classifier makes the right decision. So if it makes the right decision, it's going to choose the left if it's more probable, or the right if it's more probable. And in this case, the right is more probable because the probability of 2 plus probability of 3 is 0.6. Okay, but if we go to the right, then we're going to be choosing between 2 and 3. And then, so maybe we choose 2 that has probability 0.3, so our error rate is 0.7. If we had instead chosen to go left, our error rate would have been 0.6. Right? Okay, so this might seem like a contrived example, but I think this is actually a fairly important example for the case we're thinking about, because when you're trying to predict one of very many classes, I think often your error rates end up being quite large, just because it's a hard problem. And when your error rates are large, this counterexample starts kicking you. This kicks, right? Okay, so we might feel depressed and we might give up, but it turns out there is a solution to this. So the solution is, instead of learning from the top down with divide and conquer, you learn from the bottom up with divide and conquer. So you learn a 2 versus 3 classifier here. And then you have this critical step here. You throw away all the examples that classifier errs on. So if it always predicts 2, then you throw away all the 3s. And if it always predicts 3, then you throw away all the 2s. And if it's sometimes one, sometimes the other, you just throw away whichever examples that classifier does not agree with. And then you learn 1 versus the survivors. So, and because you're throwing away things, you have to renormalize. So it's going to be 0.4 versus 0.3, which is divided by 0.7. And ends up being the case you want to go left.
Isn't the same as like Huffman codes? This how you build it. Huffman code.
Huffman codes actually use the addition, not the max operator. So if you're doing Huffman codes, you would actually want to have this kind of code, because 2 and 3 are actually more probable than 1. But you want, instead of having the sum, you really want to have the max of the probability of 2 and the probability of 3 versus the max. You want the max of the probability of the left subtree to be compared to the max of the probability of the right subtree. So you want to recurse on a max operation rather than a sum. And this filtering operation lets you do that. Okay, so you can prove something here. You can prove that, so you have a bunch of binary classifiers, you have a distribution of the binary classifiers induced by your training process. And you can ask, what is the regret of my binary classifiers? Maybe that's some number. What is the average regret with the distribution induced by my training process? How does that translate into a regret for my multi-class classification? And not surprisingly, unsurprisingly, you can prove that log base 2 of k times the average binary regret bounds a multi-class regret. Okay, and then that's very intuitive. It's just you have log base 2 of k places to err for any individual label, and so it's a multiplier of log base 2 of k. But do you have to have a multiplier of log base 2 of k? It's kind of not clear. There's a different result I'm not really going to go into, which says that if you don't care about computational time, you can have a theorem statement like this, where the multiplier is a constant. That's the probabilistic accurating output codes paper. Anyways, we were curious about this, and eventually we found a solution. So we're taking this filter tree approach, where we did a critical second step for filtering. We're taking that for granted. And now we're going to do something a bit more complex. So imagine that we're choosing amongst 8 possible labels. You have essentially a single elimination tournament on the labels. It turns out you can have another single elimination tournament with a bit more work. You can take the loser of the first tournament and put them into the second tournament. And then there's one trick here, which is both the winner and the loser of the last match in the first tournament go into the second tournament. Then you can do it again. And now we have 3 complete single elimination tournaments. Now the question is, how many levels do we have in this structure? You can see the answer. It's 3 plus 2 plus 2. Okay, so 8 is kind of the minimum number of classes where this is kind of non-trivial. But as you get larger and larger and larger, including exponentially larger, 10 billion larger, what you'll observe is that the number of additional levels required to have an additional single elimination tournament is essentially just a constant. So that's really cool. That means that, so if you take a look at the proof statement, the proof itself, what's happening is every time you have another tournament, you can tolerate another error. And if the number of times that you can err is equal to the number of levels. So these have a constant ratio. When you have a number of tournaments like log k. So if you have a log k correcting tournament, then the multi-class regret is bounded by the average binary regret times 5.5. There's a bit more to the story here, but yeah. So I guess the bit more to the story is you have a winner here, you have a winner here, and you have a winner up there. So now we have log base 2 of k different winners. How do you robustly choose amongst those log base 2 of k? And the answer is, well, you do it like, is it in basketball? You have a tournament where, on the first round, people just play each other and the winner advances. But on the second round, maybe they play up to 3 times until somebody wins twice. And then on the next round, you play up to 7 times until somebody wins 4 times and so forth. So that kind of approach, because we've reduced it to just log base 2 of k, and things end up working out. Okay, so there's some tidying up beyond this that's required, but yeah, you can actually get a constant. It's kind of cool. Okay, so this makes us feel a bit more happy about dealing with hierarchies. So if you have some pre-existing hierarchy, you can use these kind of approaches to make things more robust or to deal with noise. But we don't have a pre-existing hierarchy. And now we need to start thinking about how do we actually build a structure. And that's pretty hard. But that's really the topic here. How do we build a structure? Okay, so the first thing we want to think about is we're trying to do a digit recognition. And obviously we want to distinguish all the individual digits. Some digits look like each other. Like so 1 and 7 are pretty confusable, especially when they're handwritten. 3 and 8 can be, well, especially if I handwrite, they can be kind of confusable. Do you prefer to split between 1 and 7 and 3 and 8 at the root? Or do you prefer to split between 1 and 8 versus 3 and 7 at the root? Right? So we want to do the hard decision at the root right here. So we're splitting 8 and 3. That's a hard prediction. Splitting 1 and 7. That's a hard prediction. Do we want to do that at the root? Or do we want to do this further down after we've already split off 1 and 7? It's kind of question you have to answer. Any votes for 1-7 versus 3-8? Yeah, 1, 2. Any votes for 3? Okay. Any votes for 1-8 versus 3-7? Right. Maybe one vote in the back. Okay. So the claim is that it's better to confuse near the leaves than near the root. And I think you have to spend some time play with machine learning to understand. But basically, you have so much representational strength in the predictor you're going to learn at any node. And if you're trying to solve a bunch of hard problems all at once, it tends to fail. So it's better to have the hard decisions be further down, where there's you have a less over-constrained predictor. Okay. Okay, so that's good. It's good intuition. But now we want to think a little bit about how do we know that we have a good partition in general? And the definition of a good partition is, I think, just fundamentally different from the definition of a good classifier. A good classifier is something which gives you a small error rate. But if I give you a partition of the examples, then I could give you the negative partition of the examples, and it would still be a good partition. Right? So that's, if I just swapped left and right on a partition, that would still be a good partition. It'd be just exactly the same quality as before. But if I try to do this with a classifier, I go from error rate 3% to error rate 97%. That would not be good. Okay, so there's a fundamental difference there that you can see between a partitioner and a classifier. And furthermore, this fundamental difference means that the problem of finding that partition is non-convex. Because here, if I have this partitioner, I have this one. If I take some sort of average of them, I actually end up getting crap. Because it's like I predict, well, you have to break the sign at 0 somehow, right? So maybe everything goes to the left or everything goes to the right. Whatever it is, it's not a good partitioner. Okay, so it's a hard problem. Nevertheless, we can still think about it in a similar way to how we think about classification in a pack learning sense. Dapnik style, not Valiant. So we can have an objective function, and we can just ask, how good is this objective function, and then what kind of convergence guarantees can we get for this objective function on a class of policies. Right, so if we have a classifier, or partitioner, which sometimes goes left and sometimes goes right, that has to be related to the label in some way. And this is an objective that we came up with that I think is a very primitive basic objective. And if you look at this, it says that we have kind of the joint probability of going right and the label. And then we have the probability of going right and the probability of the label. So this is like independence. Except our goal is going to be maximizing this. So we're trying to maximize the dependence between the left-right decision and the label. Okay? So that's a good intuition. It's a little bit helpful to rewrite this in a slightly different way because it makes it more algorithmic. So what you can do is you can factor out the probability of the label, and then you can think about just the probability of going right and the probability of going right conditioned on the label. Okay, so that's now you can think about kind of trying to evaluate this empirically or evaluating this empirically. Right, you can calculate the number of times that the classifier goes right or the number of times the classifier goes right conditioned on the label. Okay, so this is the partitioning problem. And now we want to find good partitions. And I would love to tell you that I know how to get good partitions, but in general, this is going to be computationally difficult. Nevertheless, even if we can find good partitions, there's still a question about how well do these partitions compose. Because the partition is something which happens at an individual node, and we're going to have some sort of tree-like structure. And now the question is, do we end up getting a good performance from this tree, right? So what are the systemic properties that this partition function induces? Okay, so I already told you it's non-convex. All right, so let's back up for a moment. Let's go back to what I was telling you earlier about the filtering approach. So we want to create these partitions, and we know that for filtering, at least, that's kind of a bottom-up training process. And now the question is, can you optimize this kind of objective in a bottom-up fashion? And the claim is, no, you really can't do it that way. In the end, the example is very simple. You have 3 classes. They're all sitting on a line, so you have a single feature. And if you're going to do something in a bottom-up fashion, you need to sort of pair classes randomly because you can't afford to do any kind of compare this class with every other class type of operation. That wouldn't be logarithmic time. So if you happen to compare 1 and 3, you can build a great predictor of 1 versus 3. But then you pair that with 2, and you lose. So there is no good predictor of 1 or 3 versus 2, just because you're on a line and you lose. The information is not there, at least if you're using linear predictors. Okay, so that's kind of rough. Nevertheless, I mean, even if you don't, let's go back here. Let's say we ignore all this. We ignore all this, right? So there's this counterexample. That's bad. But if it turns out to be the case that the label that's most likely has a probability greater than 0.5, this counterexample doesn't really apply. It's only when the highest probability label is less than 0.5 this counterexample applies. So let's relax ourselves a little bit. We're not going to worry about this at the moment. We're just going to try to figure out what can we do when somehow the prediction problem is relatively easy. There is a clear answer. Okay, so obviously we're not going to build from the bottom up, but we can try to build from the top down. And one way to think about this is, okay, so finding a good partition may be hard, but suppose we do find a good partition, and suppose we find a good partition recursively, then what can you prove? So we have our quality guarantee for partition, and let's say that we manage to, does this thing work? Oh, yes, excellent. Suppose we manage to achieve some performance. So 0 is the smallest this value can be. Suppose we get something bigger than 0, like gamma. This is a boosting style assumption. If we manage to achieve this gamma, then it turns out you can make a bunch of splits, and eventually your multi-class error rate will be less than epsilon. So that bunch of splits involves a bunch of things which are kind of hard to digest, but the important thing is that we have a log k. So in particular, okay, so the number of splits has this log k in the exponent. That means the number of nodes is going to be something like polynomial in k. I see, this is an additional statement you can make, which is if you have this kind of statement, then the number of levels is also going to be like log k. And that means we get a logarithmic depth structure. And that means that we can classify in logarithmic time. We haven't got to the algorithm yet, right? I mean, finding this partitioner in general is kind of hard. What's that? This is not precisely a margin. This is a weak learning assumption, I would say. So it's saying you have some edge in partitioning. So you can create a partition which purifies your class labels to some extent. Yeah, so I mean, we're assuming that it's a constant for this analysis. Okay, so this is a little bit encouraging. And now the question is, how do we actually find something with an edge? Okay, so there's a trick which is very common in machine learning, which says that, okay, so let me go back. Let's look at this. So the claim is that this is actually quite hard to optimize because it's sort of this is sort of the fraction of times, let's go back a little bit more, the computational version. This is the fraction of times you go left or go right given the label, and the fraction of times that you go right overall. So it's a very discrete number. Often what you do in machine learning is whenever you have these discrete things, you just relax that. Instead of having the indicator function of left versus right, you have some sort of margin for how far you prefer to go left versus right. And so that margin would be the y hat. And now we have this kind of softened version of optimization where we have the average score conditioned on the label being y, and we have the average score overall for our partitioner. And then the sign of the partitioner will actually induce the partition itself. Just as a common trick, it's to some extent reasonable. This is still not enough, though, actually, to make things reasonable for us, because every time you change the predictor, these numbers could change. And that would mean you have to recalculate things. So instead, what you can do is you can maintain a running average. And then if you're using a learning algorithm to form the partitioner, as the learning rate decays towards 0, the running average will converge to the expectation. And then hopefully these expectations of the soft margins will converge to the actual criteria you're interested in. What's that?
What is the running average of it?
The running average is just for each example that you encounter, you compute the score, and then you add it into the appropriate statistic. Okay, so this is an algorithm, right? And here, we're trying to come up with a way to optimize that criteria because of the boosting guarantee that we had. This is an online algorithm. For each example that we encounter, first of all, we're going to start with statistics. So we have the overall fraction, the margin for right, the margin for right conditioned on the label, and the number of things we've added into individual examples. And then for each example, if the label prefers to go left compared to the average, we're going to create a binary label, which is -1. Otherwise, it'll be a binary label of 1. And then we'll feed that into a binary classification algorithm. So this is an algorithm which operates in a reduction fashion. All right, and then we're going to update our statistics. So we just make sure that E and E sub y are updated appropriately. Okay, so this is what happens at an individual node. We know that when we compose these operators at different nodes, assuming we actually optimize our criteria effectively, we'll get something reasonable. And so you just apply this algorithm recursively. Yes, I know it quite well. The analysis for this algorithm is similar to that. So that's a binary classification version. And they're talking about boosting with the decision tree. This is doing multi-class boosting with the decision tree. And the thing which is really new here is, in terms of the theory, is that logarithmic on k dependence. All the other multi-class boosting algorithms tend to have a dependence on k rather than log k. Okay, so we have an algorithm. We can actually try it out in practice. And the question is, how does it actually work? So there's many different ways we can try to analyze this. One way is, suppose we have a fixed amount of computational time, and we just downsample as required to make one against all work with the same computational budget. Okay, and then there, it looks pretty good for us. So this is 26 classes, 105 classes, 1,000 classes, 21,841 classes, and 105,000 classes. So these are small scale compared to our real ambitions. But these are the easy data sets to get a hold of. So ImageNet, you've probably heard of. This is a vision data set, object recognition. ODP is a document classification problem. And the general story is that particularly when you have a large number of classes, we get predictive power against these classes much, much faster than one against all. It makes sense. I mean, we're trying to optimize the computation effectively. What's that? Sorry, I can't quite hear you. We're trying to get accuracy. Accuracy is big. So the bigger number wins, and generally we're the bigger number. It's good. We did some math. We came up with an algorithm, which kind of is theory-ish, and it kind of works. That's great. What's that? Oh, yeah, the bound depends on epsilon. That's true. Let's look at the, I mean, I don't know what you want. Do you want to do this calculation yourself? Yeah. Yeah, so I think often what happens is we get a pretty good gamma at nodes in the tree. There's something which this bound tells us, which is that we really want gamma to, I mean, in boosting often you think about weak learning going to strong learning. Here you really want strong binary to be going to strong multiclass, in the sense that gamma is pretty large. So gamma had better be large in order for you to succeed effectively. And I think that's just fundamentally true when you're trying to do these multiclass problems. Okay, so there's another question you can ask, which is, suppose we don't care about computational time. We just crank these things as hard as we can, optimizing learning parameters. How is our performance overall? And now, instead of accuracy, I'm looking at test error. And what we see is that, okay, so there's a random tree. This is like the divide and conquer approach that I talked about at the beginning. There's a filter tree approach where we do that filtering thing when we train from the bottom up, using just the the binary representation of the labels. And then there's this structured learning that we did, the logarithmic online multi-class tree. And what you see is that we're doing generally as well as or better than other things, and sometimes radically better. Right? So unless a Loy data set, it seems like learning the structure really matters. And in other data sets, it doesn't seem to matter quite so much necessarily. But we never lose. Maybe we lose a tiny bit there, but we never really lose. And it seems to be beneficial. Okay, so that's encouraging. But then we can also compare with one against all for the data sets where we can run that effectively. And what we see is that one against all is still doing better than us. So we're dissatisfied. Yeah, so often the number of nodes in this tree that we learn is about 4 times the number of classes, which seems to be a good number as far as having things as rich as possible, giving you the best performance possible. If you have too many nodes beyond that, you tend to overfit. Okay, so this is kind of the state of trying to get straight up logarithmic time multi-class classification to work, as far as I know. This is, okay, so, I mentioned running things on your laptop. Yeah, so you can test with the resulting classifier, and it is indeed quite fast. So it's not quite linear, which is what you would prefer, but it's linear after some sort of slowdown on the data sets that we have. And you kind of expect that because there's caching effects that come into play, basically. Okay, so in particular, for ImageNet there, this is the 22,000 class ImageNet, not the 1,000 class, which most people play with. For the 22,000 ImageNet, those classifications take half a millisecond on my laptop. Maybe faster, actually. I just got a new laptop. What's that? If you misclassify, 0, 1. Yeah, so this is the most difficult classification problem. I think often the vision people cheat by saying, oh, you get things correct if you're in the top 5, right? But, you know, you get it correct if it's the top 1. Okay, so now the question is, can we predict in logarithmic time? And the answer is certainly yes, to some extent. But there's still questions I have that I've been thinking about. One question is, can we sort of marry the filter tree with the dynamic partition, the dynamic learning of the partitions? So can we get the same sort of consistency when we have this kind of structure? I think the answer is yes, you can do that. But there's kind of a more fundamental problem, which is when you're learning some sort of tree-like representation. So in machine learning, you have some sort of balance between the representational capacity and the sample complexity. If you have too few samples, you tend to overfit, and that can kill your performance. If you have too little representation, then things are very constrained, and then that kills your performance. And now when you're learning a tree, you're sort of forced to be in both those regimes, because at the root, every example is hitting the root. And at the leaf, well, only a very few examples are hitting that leaf. So finding a better way to balance the representation complexity and the sample complexity seems like it's the key to really getting the best possible performance.
I think that for binary classification, there is dynamic programming by Kernels and also the like that paper to solve that.
Okay, so I'm done. There's a few papers here. Are there questions?